Hi everyone, thank you for joining. I'm AKM and today I'll be talking about ANQOR, which presents an anchor-based multi-class image classification framework for quantum computers. This is a joint work with Dr. Yafan, Huang, Dr. Yanyan, and Dr. Guanpeng Li. So to start with, let me start by talking about the big picture, as quantum computing is new to many of us. Machine learning today runs on classical hardware and is extraordinarily powerful. But it seems like it's hitting a wall. It's hitting a wall in terms of cost, energy, and scale. Quantum computing offers a different way of processing information. It offers a different way of representing information and also processing them through superposition and entanglement, which are properties of quantum particles. Um, Quantum machines now are cloud accessible. You can access real IBM quantum hardware through cloud, and you can run your algorithms today on them. Um, our work focuses on fully quantum implementation of a machine learning algorithm. There are many works which has been proposed on hybrid quantum framework, which does much better in terms of performance metrics. But this work actually focuses on using quantum computers entirely. But due to scale limitations and also quantum simulator compute limitation, also real hardware access limitations, we had to do minimal pre-processing, which is just PCA, to take the images, to do a dimensionality reduction of the images, and take them to 8 component vectors, which can be easily represented and computed in our quantum simulators and quantum computers. But other than that, this work mainly focuses on using a fully quantum system to do multi-class classification of images, which is possible in near future when we have large-scale quantum computers or much powerful simulators, which can process the entire images together. Then we won't have to go through a pre-processing. The challenge today with the quantum computers is with the NISQ devices. So NISQ stands for noisy intermediate scale quantum. These devices are very error prone. There is something called decoherence in quantum particles where they lose energy over time and go back to their ground state. There's T1, T2 decoherence in all the qubits. And then there is imperfect gates. So qubits are the units of quantum computation, and gates are the operations we perform on those qubits. And then we also read them out at the end to get a reading that we will use as our readout to judge the output of the circuit or the quantum system. And those readouts or measurements are also noisy. So we have 3 layers of noise there. One is decoherence coming from the qubits itself, and there is imperfect gates which induce noise in the circuits, and there is also a measurement error that we accumulate when we do the readouts. Here is a conceptual graph of how the noise builds up and also how this creates a simulator hardware gap. Now, these noises only exist in a real quantum computer. In a simulator, we don't have these noises. So our simulator performances usually show a higher number or a higher metric, but then when we switch to hardware, the performance degrades by a lot because of all these noises building up over our circuits. Now, there are some existing techniques to do multi-class classification with images on quantum computers without using hybrid approaches. An hybrid approach would wrap up classical neural network around a quantum circuit, or it would build a classical neural network before a quantum circuit and do the last processing by a quantum circuit. But all these approaches use some sort of classical network there, which kind of does a lot of heavy lifting for the quantum circuit. But in this work, we try to show that quantum circuits themselves are capable enough to do this kind of multi-class classification. And a prior work or related work to this would be Quilt. In Quilt, they use multiple readouts on circuits. They use multiple circuits or classifiers, they call them, and variants of them to do a C-class classification. So for a C-class classification, they would use a classifier in the order of C squared, which is a lot of classifiers. And also when you need variants of those classifiers, that add up to be a lot of classifiers, a lot of circuits. And also as C grows from 4, 8 to 10, the circuit and measurement counts grows quadratically. This is fine on a simulator because a simulator doesn't accumulate noise that we get in real hardware. So this performs very well on simulator, but when we switch to hardware, we see a lot of performance degradation. Now, here is our idea. Our idea starts with an anchor class. So we thought about an anchor class. If we have a multi-class, a C-class classification, we would choose one of those classes as an anchor, and then we would design C-1 classifiers around that anchor, which are all small circuits. They're shallow. We control the number of gates there. We just have one measurement per circuit. And that gives us a good system that we can deploy on a real hardware and get good readouts from them. Um, how it works is given an image, we would first have to do some PCA, that's our minimal pre-processing to get them to a dimension which we could easily fit in our currently available quantum simulators and hardware. And to encode those eight component vectors into our quantum circuits, we use a technique called amplitude encoding. Now, amplitude encoding itself is also a very expensive technique. There are other techniques like angle embeddings or angle encoding, um, which do which are less complex. Takes less gates to implement those. But amplitude encoding turns out to be the most accurate representation of classical data in a quantum system. So as we had eight components vectors, we could use amplitude encoding, and we went for that. After we have amplitude encoded the vectors into our quantum circuits, we take measurements out of them. We have C-1 circuits for our C-class classification test. So we get C-1 measurements at the end, and we perform some value aggregation. And we output our multi-class classification result. So this happens in two sectors, as you can already see. The first is the offline or the simulator, where we do the pre-processing, also the training, and then we get our tuned gates or tuned parameters for our quantum gates that we then deploy on a real hardware and run the real interface. Now, our this is how our binary classifiers look like. So the binary classifiers start by doing amplitude encoding on them. Amplitude encoding will have some gates applied on those qubits. Here we have 3 qubits, as you can see, the 3 lines on the circuit represent 3 qubits. And then there are the gates, the parameterized rotation gates. We use the Rx, Ry, Rz, the rotations along XYZ axes with our parameters that we will train for. And then we have our entangling gates. Those are the CX gates, as you can see there. And at the end, we have our measurement gate. So we try to keep everything minimal. That's why we have this layer setting where there's just 3 sets of rotation gates, and then we have our entanglement gates. And then we only want to perform one measurement here. There are many techniques you can design these kind of circuits. You can have multiple measurements, multiple gates, and a lot of other structures. So we try to do the minimal to perform this classification, this binary classification task, so that we can stack them up and do multi-class classification. The measurement here is going to be a poly Z measurement. So the score out of here, either is -1 or 1, and when we take an average of that or expectation value of that, we get the um, value in the range of -1 to 1. Um, we use two data sets for all the experiments that we have done. The first data set is the MNIST handwritten digit data set, and we also use the fashion MNIST clothing data set. We have seen that the circuit structure that we do for binary classification depends on the data. So for MNIST, which is a simpler handwritten digits data set, we only needed 2 layers without 3-qubit circuits to do the binary classification properly. But when we switched to fashion MNIST, we saw that fashion minister required a 3-qubit 3-layer setting instead of a 2-layer setting to do better binary classification. So this is also one of the findings of our study that data decides how our circuits should be designed. Um, and then when we have our C-1 classifier outputs, which land in between -1 and 1, we make an aggregation rule. Here, the rule has two knobs, which is new and tau. So the new here decides how many classifiers. It's a voting system. So new is just how many votes are required from the C-1 classifiers to classify the image as the anchor class. And tau decides what is the threshold. What is the threshold of the poly Z measurement expected value that we will choose to be our point where we decide if it's the anchor class or is the class that's being compared with it in the binary classifier. Um, so we have seen that these knobs actually help when we are trying to find the good setting for our classification task. We have seen that when we did the 10 class classification task, relaxing the new parameter or how many votes are required to classify the image as the anchor class. If we relax the new, our classification, our multi-class classification performance becomes better. And also there might be some other data sets, other settings where tuning tau can also improve performance, um, and so on. Our experimental setup, as we have talked about the data sets already, we have two data sets, MNIST handwritten data set and the fashion MNIST clothing data set. And then we have our tasks, which is a 4-class classification, 8-class classification, and 10-class classification tasks. We have our hardwares. So for the real quantum computer hardware, we use IBM Kiev and IBM Sherbrooke, which are 127 qubit Eagle R3 processors for quantum computing. And then we use only 300 image test subset. So this is because there is long queues to use these machines. And also the time that you get on these machines is very limited, so we couldn't do a larger test set. So we had to go for a small subset of 300 images. Um, the baseline that we compared to is Quilt, and then the tools that we used or for our quantum framework was Penylane, which interfaces with Qiskit to run our circuits on both the simulator and also the actual hardware. Now, the results from our simulator runs show that our technique slightly beats the baseline on the 4-class, 8-class, and 10-class classification. Remember, this is on simulator, so there is no hardware noise here. It's just pure quantum processing without any noise, error-free quantum circuits running. Um, ANQOR gives a usable 10 class result. We don't have a 10 class result for our baseline as they don't report one. And we have also found when doing these experiments that the choice of anchor class really matters. For example, for fashion minutes, the best anchor class was ankle boot. If we change to any other anchor class, the accuracy slightly drops. And then the digit 2 was the best for MNIST, where the multi-class classification accuracy was the highest when we used the anchor class of the digit 2. Here in this chart, you can see our fashion minist results on the simulator, and later we'll see our minist results on simulator and real hardware. So this real result or real hardware performance is the biggest contribution of this study. We have shown that when we deploy our multi-class classification framework from simulator to hardware, we have seen there is a predictable offset in the gap of performance when we switch from simulator to hardware. And the gap is between 18 to 20%, and this offset remains the same across classification difficulty or classification task size. So here, as you can see, for the four-class classification, we have an 18% gap from simulator to the real device performance. So the device that's been showed here is IBM Kiev. We have also results for IBM Sherbrooke, which we'll see soon. So the orange bar here is the IBM Kiev performance. And as you can see, there is like an 18%, 18%, 20% offset between the simulator and the real hardware performance, which is very interesting because if we have such predictable um, performance gaps between simulator and hardware, designing this kind of machine learning algorithms for quantum computers becomes much easier, and we can also utilize this noisy intermediate scale quantum devices to do real world tasks instead of waiting for the perfect quantum computer to come out if we have a predictable gap that we know. Um, so here in the chart, you can see the results of IBM Kiev and IBM Sherbrooke, which again shows a very predictable offset between the performance accuracies. So here you can see that the gap, the offset remains, the offset kind of depends on the error rate of the device. So IBM Kiev has a lower error rate than IBM Sherbrooke, and that's why you can see the accuracy having a fixed offset and a little better performance than IBM Sherbrooke in every single case. Here, the cases are our anchor classes. So this is for the minutes data set, and we have the digit 0 anchor class, the digit 1 anchor class, and the digit 2 anchor class. And the performance offset remains the same across all the classes. Um, One of the biggest limitations of this study is that we perform the study on very small benchmarks like MNIST and Fashion MNIST. Future work should focus on more complicated and realistic data sets. Again, we train on simulator and inference on hardware. But if we want in the near future, when we have more available quantum hardware, we can definitely train on hardware as well as inference on them. Also, our test set for the real hardware tests was very limited, which is just 300 images. And in future, we should be able to test more images on realistic data sets, which will make these frameworks stronger and better. Um, Hybrid models, which is a combination of classical neural network and quantum circuits, still have much better accuracy than all of our multi-class results. But again, in the hybrid models, people can argue that most of the heavy loading is done by the classical neural network, and the quantum contribution is not as much. That's why this study shows that quantum computers themselves are capable of performing multi-class classification and much more complicated QML tasks. We just have to design the software. We have to use the architecture as well. And probably with a predictable performance offset, as we saw in the study, we can actually use the NIST devices to do real-world machine learning tasks and help classical computers and take AI and the progress of artificial intelligence forward. Thank you, everyone, for listening.